Off in the distance, an interesting star is seen. It is a red dwarf star, and the planet we are on is a desert planet orbiting the star at an incredibly short distance. How come we haven't bursted into flames? And where is all the lava on the ground? Shouldn't this planet be a little hotter? Well, normally, being this close to a star burns almost anything to a crisp, but not with red dwarfs. The thing about red dwarfs is they are very cool stars. And no, not this kind of cool. Red dwarfs are cool in temperature, and so planets orbiting these stars can usually orbit a lot closer without burning up. What we have here is a representation of what it might look like on a planet orbiting one of these red dwarfs. And with the recent finding of TRAPPIST-1, a red dwarf star with 3 Earth-sized planets orbiting it, I thought it might be nice to take a little walk on one of these planets to see what it might be like to stare at one of these red dwarfs up close. And turns out, the view is magnificent. So, how do we know that red dwarf stars are cool? We start by looking at their spectral type. But what is a spectral type? Well, a spectral type is basically a classification for the color of a star, which can also give us the temperature as well as the luminosity. So, what spectral type is a red dwarf? A red dwarf is of the spectral type M. The color of M stars are red, of course, and also M stars are quite cool with an average surface temperature of 3,850 degrees Kelvin. But there are actually 7 different spectral types: O, B, A, F, G, K, and of course M. These range in color from bright and hot blue stars to dim and cool red stars. However, there are only 3 different spectral types that are ideal candidates for hosting an Earth-like planet. The first, if you guessed it, is the same spectral type our Sun has. It is the spectral type G. These are the yellow-white stars we are so used to seeing. Like our own Sun, these stars are very hot with an average surface temperature of 5,920 degrees Kelvin. The second spectral type is spectral type K. These are yellow-orange stars. They are slightly cooler than G stars, but are 2 to 3 times more abundant in our solar neighborhood. Their average surface temperature is 5,300 degrees Kelvin. Since they are slightly cooler than G stars, the habitable zone for these stars will be closer. The last spectral type is the M type. These are the red stars, like the one you saw at the beginning of this video. These stars have an average surface temperature of 3,850 degrees Kelvin, and so their habitable zone lies much closer than that of our own star. Since these stars are much dimmer and cooler, you would be able to look at these stars with shades on, and be able to see all the magnificent details of its surface, unlike our own Sun, which is too bright to look at. So why are spectral types so important? Well, in the last video I said scientists are able to find exoplanets by detecting the gravitational wobbles of a star due to the pulling of gravity by its orbiting planet. This is called the Doppler shift method. This, however, is not the most effective method, and there's actually a better method which is found as the most exoplanets of all the methods so far. It is called the transit method. Basically, the transit method starts by looking at a star's luminosity, the amount of light it emits, then measuring it over a period of time to see if the luminosity dips down or gets darker. If it dips down, then that could mean a planet passed in front, blocking some of that starlight. If it happens again 3 times at similar time intervals, then it is a safe bet that it is indeed a planet. With this, an observer can also measure the light particles to determine the composition of the planet's atmosphere. This is possible because when the light is blocked by the planet, as we measure the dip in luminosity, the light particles are crashing into the planet and continuing on towards us. Along the way, as the light particles hit the planet, they take with them particles from that planet's atmosphere. This is why scientists can say that an exoplanet is either rocky or full of water. And finally, I saved the best information for last. And it's kind of deep. It could be unnerving for some people, just because of the sheer probability of it. But I've thought about it and theorized about it as I've been researching more and more about spectral types and stars. And when I started researching red dwarfs a lot more, I thought of something that might be a probability. It is noted that red dwarfs can live the longest out of all the stars, and since they are much more stable and smaller and burn much slower, they can live up to 50 billion years. That's right, 50 billion. If an Earth-like planet were to orbit a red dwarf, it should, in theory, be able to have survived far longer than our Earth. And if intelligent life does indeed exist in a red dwarf star system, then they could be billions of years old. Imagine a civilization that predates our time by billions of years. Perhaps we may meet them one day, if we somehow find a way out of this star system. But until then, we're stuck here looking at the stars. So I hope you enjoyed this episode and hopefully learned something from it. Maybe your adventuring spirit for finding exoplanets is that much stronger now. I hope. But stay tuned for the next episode where we'll be discussing proof that life exists on other planets, as well as the probabilities of all that. So, this is the Lonely Spaceman. Over and out.